A lot of consumers or a lot of public that's not necessarily research oriented, I think a lot of people think about advanced manufacturing in terms of things like 3D printing. And so I'm really curious about where, for folks that have their own 3D printers, what is the connection between advanced manufacturing and 3D printing? And more importantly, 3D printing isn't just about doing stuff at home. It's doing it, in very, very secure, high volume, high cost, high scale, or large size. You talk a little bit about that, about where 3D printing has come from, where it's headed, and how it relates to advanced manufacturing.
Sure. So I think, in fact, a lot of the 3D printing, I think when you go to the industrial scale and industrial products and applications, a lot of times you're talking metal versus people at home might have the polymer or the plastic printers, which are some of the lower end and, frankly speaking, easier to address. But even on with the metal ones, so sometimes they're using powder, these so-called powder bed systems. Powders, of course, you have to be careful because you've got to have respirators on. You don't want to breathe the powders in. They can get into your skin and so forth. And then actually, I think we know you even see this with grain silos, right? There's powder that can be very, very explosive and so forth. But we're also looking at wire. So if you think about the filament that your 3D printer at home is putting out, the plastic filament, we're now looking at welding wire. So you can imagine instead of the plastic wire coming out, you take a steel or a titanium wire and you're putting that out with a weld gun. So you're actually building up the weld bead and putting that together. So now we can actually make parts out of steel. I think the exciting part, and I think what's important here is not so much that, well, we're making these parts and scaling it up, and we're going to make thousands and so forth. I think 3D printing, and we actually call it hybrid, so it's really a combination of your classic machine tool with an additive capability on it. So I can put the material down, but then I can machine it away as well. So almost like create your own casting before you go and machine it down. But I think the reality there is if you look at it, and again, I'll go back to automotive because that's a little bit of a home for me. We've been making cars for well over 100 years, and a lot of the processes have been finely honed. And so when you're looking at making hundreds of thousands of vehicles out of a plant every year, it's pretty hard to beat the processes that are in place. So one of the things actually that I'm excited about is, what happens when a new capability like 3D printing comes along? How do you figure out where that 3D printing goes into the overall value chain and production chain so that you can scale it up? And in fact, I see 3D printing as just an example of that. And what we're going to do is we're going to figure out how to integrate it both on the design and the manufacturing and the quality control and the whole life cycle analysis. And once we figure out how to integrate that, when the next hot capability comes along or new technique comes along, we'll have a pathway to integrate that directly into production very rapidly. The other one, to get back to additive, is looking at rebuilding of turbine blades. So here's the turbine blade, and the tip wears down over time. And so one of the things you'd like to do is actually machine that tip off, add material on, and then you have to machine it to blend it down. And so that's one of the things we're looking at. Now, I'll tell you some really cool stuff that we've recently put together, and these are things right now that's happening also actually in conjunction with Oakridge, is as I'm putting material down with my laser, and in this particular case we're blowing powder into a laser that's just melting the powder right on the tip of the blade. The blade is really thin, and so it's hard to get all that heat out there. So in fact, this starts to heat up, and so now we've got a thermal camera. So again, back to our digital, we're watching it. If the blade tip gets too hot, then we put a pause in the printing of the material, let it cool down. Otherwise, it just kind of melts and flops over. So really tying a lot of this together. And then in the end, we've got an entire digital record of building that blade up. So we know we're good to go there.
And so going into the future, that kind of digital record tied to every single part, no matter how small, allows to, over the lifetime of that part, allows you to integrate and learn. I think that was your point from before, integrate and learn all aspects, not just the physical part.
Yes.
That sounds like that's a good example of that.
Well, in fact, Steve, so you bring this up, so I'll extend this a little further. So it turns out these turbine blades, when they come out of service, I don't know, thousands of hours of service and so forth, they tend to warp and be bent a little bit and so forth. So they're not particularly the original shape. And so we have to measure that before we can go back and repair it. You make sure it's within spec and so forth. But one of the things I'm very interested in is you make this measurement, and now all of a sudden we're starting to build up statistics for these worn blades in terms of how they're warping and twisting and so forth. Now, the reality is I don't think I'm going to be able to zero out that twisting and warping, but I think that we're going to be able to knock out a good chunk of it so that so when you build a blade initially, you can set it up so that it doesn't warp and twist as much, which basically means your engine over its life cycle is going to have much better performance. So not only are we learning about in the process that we're doing, but inspecting the blades coming off of those engines, we're actually learning about what happened to them over their previous life.
When you think about security as it relates to manufacturing, I don't think you're talking about making sure that the physical plant is secure. I don't think you're talking about, maybe you are talking a little bit about espionage or security and safety in the manufacturing plant. It seems like because you've mentioned it so many times that security is now a major piece of not only advanced manufacturing, but all manufacturing. Can you shed more light on when you talk about security, how things have changed, and what does that mean today?
Well, so I think a couple of things. So first of all, I think it's about a third of all cyber attacks in the U.S. are against manufacturing facilities, really targeting manufacturing facilities. The bulk of those attacks are not so much to, destroy or damage or disrupt, but it's mostly to get a hold of information. So targeting getting information out of those manufacturing facilities that could provide, competition with information on how to produce things. That being said, I think you do want to make sure that certainly people don't want their equipment to be damaged. You hear, of course, about a lot of ransomware and so forth. It's one thing if your computer gets locked up and all your records are locked away, but what happens when you've got $1 million machine tool and that thing gets locked up? How do you protect that? And I think in particular on a lot of the machines, it's difficult because they really don't want you updating your Windows operating system on the machine tool. I think we've all updated our operating system and all of a sudden the printer doesn't work, right? And so the machine tool companies, for example, don't want you to do that update that often because they're not so concerned about the printer, but they're concerned about the rest of the machine not working right. But then you also have this issue of, the product could be tampered with. So if I'm making a turbine blade, let's say I could if I'm machining it, maybe I reduce the amount of coolant. So I actually burn the blade, but you don't see it, but I change the material characteristics because I've overheated the blade in the machining operation. I could even just reduce the efficiency. So instead of producing 100 parts per hour, I just dial it down to about 90 parts per hour. Nobody would be the wiser, and so forth. So, but I think there are a whole bunch of things that you have to be careful of. And again, there are just and then there are just situations where people will even just make mistakes. And so, how do you make sure that you protect your IP, you protect your equipment, and you ensure that whether it's a turbine blade or an airbag, or seat belt, when that comes out, that it's made the way it was supposed to be made, and it's going to protect somebody's life or serve accordingly and not really endanger anyone.